In this video, let's go ahead and try some practice problems that deal with factors, fractions, and exponents. Now to get the most out of this video, I encourage you to grab some paper, something to write with, and then let's go ahead and do some math together. For questions 1 and 2, we're going to go ahead and write the prime factorization for each of these numbers in the numerator and denominator. Then we're going to use those prime factorizations, then go ahead and simplify the original fraction. Okay, so for number 1 here, looks like we have these two numbers 168 and 224. So let's go ahead and start with 168. Now I'm going to use a prime factorization tree just to kind of make this super clear. So 168 is even, so I'm going to divide it by 2 first. So I'm going to say 2 times 84. Now, 84 is even again, so I'm going to divide this by 2, and that's going to be 2 times 42. Now, 42, that is divisible by 6 and 7, so I'm going to go ahead and say 6 and 7 here. And then 7's prime, but 6 can be broken down into 3 and 2 here. So these would be all the little numbers that we'd put in our little prime factorization tree here. So we have our prime factors here of 2, 2, 3, 7, and 2 for 168. So writing this prime factorization, we can say this 168 is equal to 2 times 2 times 2. There's 3 of those, right? And then times 3 times 7. Now feel free to use exponents if you want as well, but I'm just going to go ahead and write it out expanded here, right? So for 224, let's go ahead and break that down. It's an even number, so I'm going to divide it by 2 here. That's going to be 112 or 112. 112 is even again, so I'm going to say 2 and 56. Now 56 can divide by, I guess I can do 2 again, but I could do 7 times 8 here. Do 7 times 8. 8 can break into 4 times 2, and 4 can break into 2 times 2 here. All right, so what are our prime factors? We have 2, 2, 7, 2, 2, and 2. So it looks like there are a total of 5 2's. So the prime factorization here, I'm going to say here is 2 times 2 times 2 times 2 times 2, and then times 7. Okay, so if we're going to go ahead and write those prime factorizations, we might as well see what common prime factors they have, so we can find out the greatest common factor pretty easily here. So they have a 2 in common, another 2 in common, another 2 in common, as well as a 7 in common here. So if you go ahead and multiply all the common prime numbers, you get the greatest common factor. So 2 times 2 is 4, times 2 is 8, times 7 is going to be 56. So the greatest common factor is going to be 56. So I'm going to go ahead and write that here, that the GCF of the numerator and denominator is 56. Now, if we go ahead and just show that we're using the greatest common factor, we would just divide both of these by 56, right? Basically, 168 divided by 56 is just going to be 3 on top. So that's going to be that leftover number. And then in the denominator, the 224 divided by 56 is just going to be 4 here. So at the end of the day, this 168 over 224 is really just the same value as 3/4. All right, so let's try another one, another similar type of problem. Let's go ahead and see if we can break these down. If you feel like you got the hang of it, feel free to pause the video and try it on your own to see if you can do it fluently as well. 195 isn't divisible by 2. You could divide it by 3, but I think 5 is going to come a little bit easier to most people here. I think it's going to be 5. I know 5 times 40 is 200, so 5 times 39 must be 195. 39 is divisible by 3. Looks like 3 times 13. So here are our prime factors. I think it's just going to be 5 times 3 times 13 here. So I'm going to go ahead and say it's going to be 5 times 3 times 13. Feel free to write them in order from least to greatest, or any order that you'd like here. 234 rather. Let's see, if we go ahead and break this down, I'm going to start with a 2 here. I think that's going to be 117. For 117, you can't divide by 2, but you can divide by 3. You can also divide by 9, so really your call here. I know 9 times 10 is 90, which 27 left over, so it goes in 3 times. So I'm going to go with 13. And then 9 here can break down into 3 times 3. So I think our prime factors here are going to be 2, 3, 3, and 13. So I'm going to go ahead and write that prime factorization of 2 times 3 times 3 times 13. Okay, so what common prime factors do we see? I think we really just have the 3's in common as well as the 13's in common. So the greatest common factor between the numerator and denominator looks like it's going to be 39 if you go ahead and just multiply 3 times 13 together. Okay, so if that's the greatest common factor, then we can go ahead and divide both the numerator and denominator by this common factor. And if you divide this 195 by 39 on top, you're going to be left with 5 here. Hopefully that makes sense. It's a leftover prime factor. And then on the bottom here, we have 2 times 3, which is going to be 6. So that's going to be the denominator here. All right, let's check out number 3 and 4. Let's switch gears just a little bit. Here we're going to factor each of these monomials that we see in numerator and denominator. Then we're going to go ahead and simplify the fraction using the GCF we can find between these two monomials. So I'm not going to go ahead and make trees for these coefficients just because these numbers are a little smaller. 16 I know will break into 2 times 2 times 2 times 2. X cubed is going to break into x times x times x, and then y squared is going to break into y times y. So that's the factored version of the numerator. And then for the denominator, I know 48 is going to break into 2 times 2 times 2 times 2. There's going to be 4 2's, that's 16. 16 times 3 is 48. The x squared will break into x times x, and the y to the 4th will break into y times y times y times y. So if you're going to go ahead and simplify this expression, let's see what common primes they have here. We have a 2 in common, a 2 in common, another 2 in common. Looks like they have 4 2's in common. The 3 is not in common there. Looks like they're going to have 2 x's in common as well as 2 y's in common, right? So if you want to find the greatest common factor here, looks like it's going to be 2 times 2 times 2 times 2, which is 16, times x squared, because x times x is x squared, and then y times y, which is y squared here. So the greatest common factor, I'm just going to write it to be a little bit more clear, between the numerator and denominator is going to be 16 x squared y squared, right? That's the greatest factor that would go into both the numerator and denominator, so that means we must be able to divide top and bottom by that monomial expression here, okay? So if we go ahead and divide top and bottom by 16 x squared y squared, what would we be left with? Well, it's just going to be, you can kind of see these little factors left over. That's going to be what's left here. So the numerator is actually just going to be 1x, or just x, and the denominator is going to be 3y squared. Okay, so that would be the most simplified expression. There's a lot going on here, so I'm just going to put this in a box so it's a little bit more clear where my simplified expression is. All right, for number 4, let's go ahead and try another similar type of problem. So we have this numerator of 45a cubed. I know 45 breaks into 9 times 5, and 9 breaks into 3 times 3, so it's 3 times 3 times 5. And then a cubed just breaks into a times a times a. For 75, I know that's going to be 3 times 25. And then 25 will break into 5 times 5. And then the a to the 5th power is just going to be 5 of these a's multiplied together. 3, 4, and 5. And then there's going to be 2 of these b's multiplied together. Okay, so what do they have in common between the numerator and denominator? Looks like they both have a 3 in common as well as a 5. And then it looks like they're going to have 3 of these a's in common. And they don't have any b's in common, so don't worry about the b's. So what's the greatest common factor here? Well, 3 times 5 is 15. 15 times a times a times a. Let's go ahead and write that over here on top. The greatest common factor here is going to be 15a to the 3rd power. So, of course, that means the numerator and denominator can both divide by this 15a cubed on top and on bottom because it's the greatest common factor between them. And what are we left with? Well, on top, we're going to be left with a 3. And on the bottom, we're going to be left with this 5 times a times a times b times b. So there's a lot more in the denominator here. So I think we're just going to have 3 on top. And in denominator, we're going to have 5a squared times b squared. So this right here would be our most simplified expression after dividing both the top and bottom by the greatest common factor of the numerator and denominator. All right, let's try some different types of problems. Here we're going to go ahead and try practicing our operations with fractions a little bit, applied to some geometric types of problems. So for number 5, we're going to go ahead and find the perimeter of a rectangle if we know the length and we know the width. So let's go ahead and just set up an equation here. So perimeter, or capital P, is equal to 2 times the length, which you know is going to be 5 and 5/6. And then let's go ahead and add on 2 of these widths. So it's going to be 2 multiplied by this 8 and 7/8 here. Okay. Now, if we go ahead and figure out the perimeter here, we can turn these into improper fractions and then multiply, or we can just double the mixed numbers, and that might be a little faster in this case. Just be careful with what you're doing. So if you go ahead and double this 2 times this 5 and 5/6, if you double 5, that's going to be 10, and if you double the 5/6 part, that's going to be 10/6, right? Make sure you don't touch the denominator there, leave that the same. And then if you go ahead and double 8 and 7/8, that's going to be 16 and 14/8, right? So again, if this is a little uncomfortable, feel free to go to improper fractions, but I think this might be a little faster. We have these improper fractions inside of mixed numbers. It's just temporary. The 10 and 10/6 is really just 11 and 4/6. And then the 16 and 4/8 is essentially just 17 and 6/8 here. Okay. Now, both of these fractions can be simplified a bit. So it's gonna be 11 and 2/3. And let's go ahead and add on this 17 and 3/4. And if we go ahead and just turn these into common denominators, we can say this is gonna be 11, using the least common denominator, it's gonna be 11 and 8/12 plus 17 and what? I think that's 9/12, right? Now, if we go ahead and add these together, adding the whole numbers together, 11 plus 17 is going to be 28. And then 8 plus 9 is going to be 17. So we're getting 17/12. And then this is an improper inside a mix. So we can regroup here and call this 29 and 5/12. Okay. So in this case, we can go ahead and say the perimeter is going to be 29 and 5/12 meters. All right, let's check out number 6. For number 6, let's go ahead and see if we can find the width of a rectangle if we know what the perimeter is going to be. It's going to be 45 and 3/4, and we know the length is going to be 14 and 5/6 yards. All right, so we know the perimeter. The perimeter we're just going to go ahead and write here is going to be 45 and 3/4. This is going to be equal to 2 times the length. We do know the length. The length here is going to be 14 and 5/6. And then we don't know the width yet, so we're just going to say this is going to be 2 multiplied by W, or just 2W here. Okay, let's go ahead and clean this up a little bit. We're going to leave this 45 and 3/4 over here on its own for a moment. And then let's go ahead and say if we double this 14 and 5/6, if you double 14, that's going to be 28. If you double the 5/6, that's going to be 10/6, right? And then we're going to go ahead and add this 2W on afterwards. Okay, now if we know that this is equal to this fraction plus this 2W, then 2W must be equal to this 45 and 3/4 minus this 28 and 10/6. So I'm going to go ahead and rearrange this a little bit here. I'm going to say if you do 2 times the width, that's going to be 45 and 3/4 minus, and I'm also going to go ahead and just rearrange this a little bit and regroup it. So it's going to be 29 and 4/6, but 4/6 just simplifies down to 2/3 here, right? So doing a couple steps in one just to save a little bit of writing, but hopefully it makes sense that we should simplify the fractions as we go a little bit as well. Okay, to go ahead and subtract these 2 fractions here, we want some common denominators. So we know if you do 2 of these widths, that's going to be equal to 45, and let's go ahead and go to 12ths here. So it's going to be 9/12 minus 29, and I think this is going to be 8/12, right? All right, so let's go ahead and subtract these now. If you have 2 of these widths, that's going to be, this is nice to subtract just because 9 is bigger than 8 and the 45 here is bigger than 29. So subtracting the whole numbers here, I believe we're going to get 16. And subtracting the fractional parts, we're going to get 1/12 here. All right, so we now know that 2 of the widths is equal to 16 and 1/12 yards. So what's one of these widths? Well, to get the width, we're just going to go ahead and take, if we know 2 of them is 16 and 1/12, we should go ahead and divide it by 2. All right, so let's go ahead and say if we know it's divided by 2, we could also say we can take this and multiply it by the reciprocal, right? So let's go ahead and turn 16 and 1/12 into an improper fraction. So 16 times 12 is going to be 192, plus 1 is going to be 193. So we have 193 over 12. That's just the improper version of that 16 and 1/12. And instead of dividing by 2, let's go ahead and multiply by 1/2 here. Okay. Now, if you go ahead and do that, we're going to find out the width here is going to be 193 times 1 is 193, and 12 times 2 is going to be 24. Now, how many times does 24 fit into 193? Just do a little bit of long division or do some multiplication on the side there. I think you should find out it goes in 8 times. 8 times 24, I believe, is going to be 192. So it's so close to 193. So it's going to be 1 over 24. And hopefully this makes sense, because if you take half of 16, that's going to be 8, and half of 1/12 is going to be 1/24. So I hope that kind of makes sense. So you could have done that as well if you noticed that as well. All right, so we can go ahead and say. All right, let's go ahead and try number 7. In number 7, let's go ahead and find the area of a rectangle if we're given the length and the width. So the formula is area is equal to length times width for a rectangle. So we can go ahead and say here that the A, or capital A, area is going to be equal to the length, which we know is going to be 5 and 5/6. Let's go ahead and multiply that by this 9 3/5. All right, so let's go ahead and first actually just turn these mixed numbers into improper fractions. So 5 times 6, that's going to be 30. 30 plus the 5 is going to be 35/6, right? And let's go ahead and multiply this by the improper version of this one. So 9 times 5 is 45. 45 plus the 3 is going to be 48. So we're looking at 48 over 5. So let's see. For multiplying fractions here, we could multiply then simplify later, or we can go ahead and see if we can cross cancel now. So 6 and 48, their greatest common factor is 6, so we can divide them both by 6 to get 1 and 8. And then if we go ahead and look at 35 and 5, their greatest common factor is 5. So dividing them both by 5, we get 7 and 1 on the top and the bottom. So turns out here, 7 times 8 on top is 56. So we have 56 over 1, which is really just 56. All right, let's go ahead and check out another one. For number 8, we're going to go ahead and find the length of a rectangle if we're given the area of 14 2/3 square inches and the width of 2 1/5 inches. All right, so plugging in the area, we're going to say that's going to be 14 2/3, and that's going to be equal to the length. I'm going to use a cursive L for the length, multiplied by the width here of 2 1/5. Now, if we know that the length times 2 1/5 is equal to 14 2/3, then we should be able to rearrange this and say that the length here is going to be equal to 14 2/3 divided by this 2 1/5, right? Hopefully that makes sense. But that means that we can go ahead and just rewrite this as well and say, for dividing fractions, we can turn them both into improper fractions. So 14 2/3 is going to be 42 plus 2, that's 44 thirds. So that's going to be 44 over 3. Divided by, and let's see, this 2 1/5 as an improper is going to be 10 plus 1, so 11 over 5. Okay, now it turns out when you are dividing fractions, right, we can rewrite all division problems as multiplication problems as long as we multiply that first value by the reciprocal of that second value or fraction here. So in this case, it's going to be 44 thirds multiplied by 5 11ths. Now, just like earlier, you can just multiply and then simplify later, but I see this 11 and 44 have a nice greatest common factor of 11. So if you divide them both by 11, we'll get 4 and 1 on the top and the bottom. So if we just go ahead and multiply now, we get much nicer numbers here. So we're going to get 20 thirds here. All right. Now, just cleaning this up a little bit and writing it as a mixed number, the length here, 3 goes into 26 times with 2 left over. We're looking at a length here of 6 2/3 inches. All right, let's shift gears a little bit here and let's try dealing with some exponent properties and exponent rules here. All right, so for number 9, it looks like we have a product here. We're gonna go ahead and see if we can write all our final expressions only using positive exponents. First things first, let's go ahead and multiply the normal numbers here, these coefficients. So rearranging this, I'm just going ahead and write this is 5 times 2 times y to the 4th power times y to the negative 8th power, right? Just to clean that up a little bit, that's using the commutative property, just rearranging multiplication. 5 times 2 is just going to be 10 though, right? And then we can use the product of powers property and say we can rewrite this y to the 4th times the y to the negative 8th. We can add those little exponents of 4 negative 8 to get negative 4. Okay, now we were instructed to write our final expression using only positive exponents, so keep in mind that this y to the negative 4th power is really the same thing as 1 over y to the positive 4th power, right? It just means that's the reciprocal. So we can go ahead and write our final expression here as a 10 over y to the 4th power, right? That would be our most simplified expression here using only positive exponents. All right, let's check out number 10. For number 10, I'm going to go ahead and expand this so it's a little bit more clear, but we have this 5x to the 3rd power, and we're going to multiply this by another 5x to the 3rd power. That's really what this little 2 on the outside means. It means there's 2 of those, right? So you can also think about this as, okay, we can rearrange and say it's 5 times 5, and we can say it's like x to the 3rd power times x to the 3rd power, right? Cleaning this up a little bit, we're going to get 25 in front, and then using that product of powers property, we can get 3 plus that 3, which is going to be 6, right? And of course, if you prefer to use the power of powers property because that makes sense to you, then you can say this 2 can be applied to this 5, so it's 5 squared, which is 25 here. And then if you go ahead and square this x cubed, there's 2 of those multiplied together, you do get this x to the 6th power here. So this would be our most simplified expression, and we don't have to worry about any negative exponents for this expression. All right, let's check out number 11. For number 11, same thing. I'm not going to go ahead and use the power to a power property. Instead, I'm just going to go ahead and expand this in case it's more clear to some people. But really, we have this negative 2x to the third power multiplied by another negative 2x to the third power multiplied by another negative 2x to the third power. Okay. Now, we could rearrange this as well. This is really just going to be negative 2 multiplied by negative 2 multiplied by negative 2, but I'm just going to go ahead and write right now that's going to be negative 8. And then if we multiply this x to the third power times x to the third power times x to the third power, you would add 3 plus 3 plus 3, and that's why the power of a power property works. You get x to the 9th power here. So this would be the most simplified expression. All right. Again, the directions do say to not write any negative exponents, so the negative 8 here is fine because it's not an exponent. If you wanted to use the power of powers property, this 3 can be applied to the negative 2. So keep in mind it's negative 2 times negative 2 times negative 2. And then 3 times 3 here as a shortcut does get you x to the 9th power. All right. Let's check out number 12. In number 12, we have a quotient here. So it looks like a fraction. In this particular case, I'm going to use the power of power property just to save a little bit of time. Hopefully it made sense if you expand it. And if you like expanding it, keep doing that. This 2 is applied to this 3 here. So it's going to be 3 to the second power, which is going to be 9, right? And then we're going to have this y to the 5th power times another y to the 5th power. So in total, that's y to the 10th power. If you add 5 plus 5 or do 5 times 2, your choice of how you want to think about it. In the denominator, I'm not going to do anything just yet. I'm just going to write 12y to the negative 5th power. Okay. Now, let's go ahead and just simplify the fractional part. So if we look at 9 and 12, they can both be divisible by 3. That's the greatest common factor. So I think that's going to be 3 over 4 in terms of those numbers, those coefficients there. Now, for this y to the 10th power over y to the negative 5th power, you can go ahead and use that quotient property and subtract 10 minus this negative 5, which is really just going to be 10 plus 5, which is going to be 15. So we're really looking at this being multiplied by y to the 15th power, right? By default, it's always going to be on top, so you can rewrite this as 3y to the 15th power all over 4. Okay, so this right here would be our most simplified expression. All right, let's check out number 13. For number 13, looks like we have a product here. I'm gonna go ahead and rearrange this a little bit so it's more clear. Let's see, we have this negative 3. We're also gonna be multiplying it by this negative 2. So I'm gonna multiply by negative 2 and use parentheses just so it's a little bit more clear. Then we're gonna be multiplying this by y to the negative 7th power, multiplied by y to the negative 3rd power. All right, so negative 3 times negative 2 is going to be positive 6. And then if we use that product of powers property, we can add that negative 7 plus negative 3 to get negative 10. All right, now this is a simplified expression. However, it's not written using only positive exponents. So we can also rewrite this as 6 multiplied by 1 over y to the 10th power, which we can also say is just going to be 6 over y to the 10th power, just kind of writing it as one fraction. Okay, so this right here would be the most simplified expression using positive exponents only. All right, for number 14, you want to be careful with this one just because we have a negative exponent on the outside. I think the easiest way to deal with this is because the entire thing is being raised to a negative exponent, what you can do is just take the entire expression and move it to the denominator. So we can just go ahead and say this is going to be negative 3y to the 2nd power raised to the positive 3rd power once you have written the reciprocal here. You could also use the power of powers property and go ahead and apply this negative 3 to both of these, but then you would end up flipping both of them to the bottom anyway, but feel free to do it that way if you prefer. If you go ahead and then evaluate this, I prefer to use the positive exponents here, right? So I'm going to have 1 over, and then we have negative 3 to the 3rd power. So I'm actually just going to write it out to be a little bit more clear because there's a lot of moving parts here. So it's negative 3 to the 3rd power times y to the 2nd power times 3, right? Because there's 3 of those. So 2 plus 2 plus 2 or 2 times 3. It all sounds good, whichever way you want to kind of write it there. So rewriting this and simplifying a little more, this negative 3 to the 3rd power is negative 3 times negative 3 times negative 3, which hopefully makes sense is going to be negative 27. And then if we have this y to the 2nd power to the 3rd power, that's really y to the 6th power here. Okay, so writing our final expression, typically we move the negative in front of the fraction. So it's going to be negative 1 over 27y to the 6th power. All right, this right here would be our most simplified expression. All right, in number 15, this one looks a little bit scarier because there's so many moving parts here. There's so many little exponents and things to look at. But take a look at the second part here. This whole second part is raised to the 0th power. So that actually means that this entire part of the expression, this is actually just equal to 1 because the entire thing's raised to the 0th power, right? So you can actually just pretend that's going to be a 1 right now, or you can do it later, up to you. What I'm going to do is just focus a little bit just on this first part here. It has this negative exponent, which is kind of similar to what we had in the last expression. So I'm going to go ahead and flip the entire thing so we don't have that anymore. So I'm going to say it's 1 over 2x to the 4th power, and I'm going to raise that to the 2nd power. Okay. Now, for the second part, I'm just going to write it as 1, so it's very clear that this expression here I just rewrote like this, the reciprocal raised to a positive exponent here, and then this entire thing was raised to the 0th power, and anything to the 0th power is equal to 1. All right, so let's go ahead and clean this up a little bit. Anything times 1 is going to stay the same, so 1's going to be on top here, and then let's see on the bottom here, it's going to be 2 squared, right? We're going to say we can use the power of powers property, or we can expand it, whichever one you prefer. But 2 squared is going to be 4, and then x to the 4th power raised to the 2nd power is going to be x to the 8th power. The shortcut is just multiplying 4 times 2. But if you want to use the other property where we have a product of powers, it's 4 plus 4. So this right here would be our most simplified expression. So it looked a little scary in the beginning, but hopefully if you knew what to do with that 0 exponent, you could have saved some time there. All right, for number 16, we have another rational expression here. So let's go ahead and break it down piece by piece. What you can do here is, let's go ahead and look at just the coefficients first. This is 4 and 8. You can divide 4 and 8 both by 4, so you're going to get 1 and 2. I'm actually just going to write the 1 and 2 for now. Okay, top and bottom. And then if we go ahead and move some of these exponents, this x to the negative 4th, we can move it down, and we can move this x to the negative 5th up, right, if that makes sense. You could subtract right away using the quotient property, but I'm just using our property of negative exponents first. So again, there's no one perfect way to do this. There's a few different strategies that might be more or less clear to different people. So I'm just going ahead and rewrite this so we only have positive exponents. And then I'm going to use our quotient property just because I think it's easier to subtract positive numbers than negative numbers, right? But again, totally your choice. I'm going to drop the 1 because it's and 1 times anything is just going to be that, whatever that is. Now, when we have this x to the 5th power over x to the 4th power, we can use the quotient property and subtract. 5 minus 4 is 1. So we're going to have x on top of our expression here. And then we can go ahead and use the quotient property again. 2 minus 7 is going to be negative 5. So we can write this as y to the negative 5 power. Right, if you just are subtracting, it's going to be on top though, right, by default. We're going to have this 2 on bottom. And then if you go ahead and use our negative exponents property, we can say this is going to be x over this 2y to the 5th power, right? And if you just went right ahead and said you knew that there was going to be 5 left on bottom, if you're cross-canceling using GCFs, that's fine too. But I'm just going ahead and showing a few different ways to kind of go ahead about this using different properties here. All right, so this right here will be our most simplified expression using positive exponents only. And for the last set of problems for this practice session, we're going to be dealing with some scientific notation. All right, so for questions 17 through 20, we're going to go ahead and write each of these numbers that are in standard notation in scientific notation, or standard form rather. So let's go ahead and take these really big numbers or really small numbers, write them in scientific notation here. So for this first number, it's going to be a big one here. Let's see, if we go ahead and count how many times we're going to move it over, by default, the decimal is at the end of the number to the right because it's a whole number here. So we're going to move over 3 and then 3 and then 3. And this is where we're going to stop because we need only one whole number. So this value here is going to be 5.1. All right, so 5.1 multiplied by 10 to the, and then how many times would we move over? Well, we made it 1,000 times smaller, 1,000,000 times smaller, 1,000,000,000 times smaller. So it's going to look like we moved over 9 times. So it's going to be 5.1 times 10 to the 9th power here. For number 18, let's go ahead and see how many times we have to move this decimal to get a whole number. But we know what we're going to have at the end here, 8.97. If you just take a look at their digits at the end of the decimal, and let's see how many times you have to move this decimal to get there. So let's see, we're going to move over 1 time, 2 times, 3 times, 4 times, 5, 6, 7, 8, 9, 10, 11. So I believe this is going to be 8.97 times 10 to the negative 11th power here. All right, for number 19, let's see, this is gonna be another big number, so we need a positive exponent here. So let's go ahead and just write down, first we have 8.34. All right, this number has to be between 1 and 10 here, and it's gonna be times 10 to the, and just in your head, just kind of make sure we know we're gonna be using a positive exponent here. But how many times are we gonna move? Well, it's gonna be 3, 6, 9, 12, and then one more makes 13. So it's gonna be 8.34 times 10 to the 13th power. For number 20, we have a very small number here. We need one whole number at the end, so we're going to move the decimal until it says 5. So you can write 5.0 or just 5 times 10 to the, and I'm just going to put a negative number here because I already know it's going to be negative. Let's see how many times we're going to move here. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So I believe this is going to be 5 times 10 to the negative 16th power. All right, so now that we got some of the basics out of the way of how to write big and small numbers using scientific notation, let's try a few application problems where we kind of use these in some different contexts. So the SR-71 Blackbird is one of the world's fastest airplanes. It's capable of traveling at a cruising speed of Mach 3 or 3 times the speed of sound. The speed of sound is approximately 7.6 times 10 to the second power miles per hour. What is Mach 3 in miles per hour? We're gonna go ahead and write our answer in scientific notation. And so we know the speed of sound here is going to be 7.6 times 10 to the second power. So that's the speed of sound. But this Blackbird is going to be traveling 3 times the speed of this. So it's going to be multiplying this by 3, right? We can go ahead and rearrange this, but this is going to be our original expression here. We can say this is going to be 3 multiplied by 7.6, and then multiplying that by 10 to the second power. Now, if we go to multiply 3 times 7.6, I believe that's going to be 22.8. So we're going to go ahead and say this is going to be 22.8 multiplied by 10 to the second power, right? But then we can also rearrange this a little bit and say this is going to be 2.28. If we make that one, that value 10 times smaller, we should multiply it by 10 to the first power, then multiply that by 10 to the second power. And so just to be clear here, this 22.8 that we had, we just rewrote it as 2.28 times 10 to the first power, just because we're trying to write this in scientific notation. And then using our product of powers property, we can say this is going to be 2.28 multiplied by 10 to the third power. If we go ahead and just multiply these two powers together and use that shortcut and add those exponents. And so in conclusion, we can say that Mach 3 is going to be 2.28 times 10 to the third power, or 2,280 miles per hour. All right, so in 22, we see that Earth has a mass of 6 times 10 to the 24th power kilograms. If the star Tau has an exoplanet that is about 2.5 times 10 to the 3 times as massive as Earth, what is the mass in kilograms of Tau exoplanet in scientific notation? And so we're going to go ahead and start off with the mass of Earth, which is going to be 6 times 10 to the 24th power. And then we're going to go ahead and see, we know the exoplanet here is going to be 2.5 times 10 to the third power times larger. So we're going to just multiply these two expressions in scientific notation here. Of course, we can go ahead and rearrange this. So it's going to be 6 multiplied by 2.5. And then multiply by 10 to the 24th power times this 10 to the third power. Okay, let's go ahead and just multiply the 6 times 2.5. Now if we go ahead and multiply 6 times 2.5, well 6 times 2 is going to be 12 and 6 times 0.5 is 3. So 6 times 2.5 should be 15, right? So we're going to go ahead and write this is going to be 15 multiplied by 10 to the, and then use that product of powers property and add those exponents. 24 plus 3 is going to be 27. Now 15 can be also written as 1.5 times 10 to the first power, and then we can leave that 10 to the 27th power alone for a moment. And then using that product of powers property again, we can say this is 1.5 times 10 to the 28th power here. And so the mass of this exoplanet would be about 1.5 times 10 to the 28th kilograms. Let's check out number 23. In 23, we see the half-life of uranium-238 is 4.5 times 10 to the 9th power years, and the half-life of uranium-234 is 2.5 times 10 to the 5th power years. The question is how many times greater is the half-life of uranium-238 than that of uranium-234? And so while it's not super important for this problem, uranium-238 and 234 are just different types of isotopes of uranium that can be found around. Then the half-life is just how long it's going to take for it to decay over time. And it's going to take 4.5 times 10 to the 9th years to have half as much as what we started with for uranium-238. And the half-life for that uranium-234, it's going to take 2.5 times 10 to the 5th power years for that to have half as much as what we had in the beginning. So that's just, in a nutshell, what half-life is. So when it says how many times greater is the uranium-238 than the uranium-234, we're going to go ahead and divide. And hopefully that makes sense, because if you think about, if I say how many times greater is 10 than just say 2, you would say it's 5 times greater. That's because 2 times 5 does equal that 10. So to get how many times greater, let's take the larger one here, the larger value of, let's see, it's going to be 4.5 times 10 to the 9th power. Let's go ahead and divide that by this 2.5 times 10 to the 5th power. All right. Now we can go ahead and use a property of fractions where you can separate the factors here and say it's going to be 4.5 over 2.5 and multiply this by this 10 to the 9th power over 10 to the 5th power. So you can just kind of deal with the decimals and the exponents a little bit separately here, right? Now, when you take this 4.5 divided by 2.5, you can really just think about that as 45 over 25 if you just multiply top and bottom by 10. And then if you divide them both by 5 there, you're going to get 9 over 5. So this ends up being 1 4/5 or 1.8. So I'm going to go ahead and say that this is going to be 1.8 times 10 to the what power? Well, if you use that quotient property, you can say 9 minus 5 is going to be 4. So we're going to have 1.8 times 10 to the 4th power. So when we say that it's 1.8 times 10 to the 4th power times greater, we're saying it's that many times longer for the half-life of one of those isotopes than the other one. And if you're wondering how many years this is, kind of you can think about it as you move over 1, 2, 3, 4. And if you add 3 zeros in here, we're talking about 18,000 times longer. All right, so it's quite a bit longer than the other one. All right, let's check out number 24. For number 24, we see the mass of an electron is about 9.11 times 10 to the negative 31st power kilograms, and the mass of a proton is about 1.67 times 10 to the negative 27th power kilograms here. So the question is, how much heavier is the mass of a proton compared to the mass of an electron? So if you're trying to find out how much heavier something is than something else, you would just go ahead and subtract their weights, right? So we're going to do the same thing here. If you're trying to see which one's heavier, well, the proton here is definitely heavier than the electron here, because you can see it has a greater exponent. Remember, negative 27 is greater than negative 31. So we're going to take this larger weight of 1.67 times 10 to the negative 27th power. And let's go ahead and take that and subtract this other weight of 9.11 times 10 to the negative 31st power here. Okay. Now, when we're going in and subtracting numbers in scientific notation, our goal is to get both of the degrees of 10 to be the same here, right? So let's go ahead and do that. We're going to choose to make them both the greater exponent here. So let's go ahead and change this 10 to the negative 31st power. It needs to get 10 to the 4th times power bigger to get to this 10 to the negative 27th power. So let's go ahead and say it's going to be 1.67. Let's kind of leave this one alone for now, times 10 to the negative 27th power. And let's go ahead and say it's going to be minus. And let's see, if we're going to make this one 10 to the 4th times bigger, we need to make it 10 to the 4th times smaller for this 9.11. So we move it over 1, 2, 3, 4. We'll put the decimal here. We need to add 3 zeros. So it's going to be, let's see, 0.000911. But now if we made that one, what is that, 10,000 times smaller, then we're going to make this one 10,000 times bigger. Say this is going to be times 10 to the negative 27th power. All right, so at this point, we do like the fact that we have these times 10 to the negative 27th power. And once those match, what we can actually do is we can actually go ahead and write the decimals here, 1.67, and subtract this 0.000911. And we can go ahead and multiply that by 10 to the negative 27th power, since they're both raised to the, both multiplying by 10 to the negative 27th power. So if you know a bit of a distributor property or just kind of properties of factoring a little bit, you can see that that is going to be okay to write just because they're both being multiplied by 10 to the negative 27th power. Okay. Okay. Now, if you go ahead and subtract these decimals, just make sure we go ahead and line up the decimals to go ahead and do so. But it would be 1.67. This one only has 2 decimal places, so you'd have to go ahead and add 4 zeros after it to then go ahead and subtract here. So what you can do is when you subtract 1.67, subtracting that whole thing here is going to be 1.669, and then it's going to be 0.89. This is going to be the whole thing is being multiplied by 10 to the negative 27th power. And so what we just found out is a proton is about 1.67 times 10 to the negative 27th power kilograms heavier than the mass of an electron. All right, so there you have 24 different practice problems dealing with some factors as well as some fractions, and then we also dealt with some different types of exponent properties and rules, finishing up with some scientific notation applications. So hopefully you found the video helpful. If you did, please consider giving the video a thumbs up and sharing with a classmate or friend who might also find it helpful. And as always, keep up the great work that you're already doing, and I'll see you in the next one.